Hi, this is the one page or the one picture proof of Fermat's last theorem. And this is actually the picture. We say that because x to the n plus y to the n is equal to some z to the n, where these are x, y, and z are all integers, we can construct a right triangle up here. Okay? And we can take x to the n over 2, y to the n over 2, and make two legs of a right triangle. When you square everything by Pythagoras' theorem, you end up with z to the nth. So we can construct this right triangle. But so x to the n may be some number, this is what we're supposing, a whole number, but we don't know that x to the n over 2 is a whole number or not. It most likely is not. So we have to consider that. But there is an absolute value of x to the n over 2, which is an integer. And there is an absolute value of y to the n over 2, okay, that is an integer. But the sum of but xn over 2 most likely is smaller than x to the n over 2, because x to the n over 2 may have a remainder after the period. Okay, so we can construct this right triangle. Okay, but x to the n, y to the n, our absolute values are explicitly integers. Okay, and we come up with the conclusion that the absolute value squared plus x to the n over 2 squared plus y to the n over 2 squared is less than z to the nth, because you're not including the remainders in the summation. So if x and y are integers, okay, then the absolute value of x to the n over 2 is just when it's squared, is just x to the n, because the remainder is missing, or it's just 0. But that means then that the alpha is equal to 0. And n is equal to. For instance, if you have 10 to the 4th, okay, then really 10 to the 4th is just 100 to the squared. So that even though it seems to be more, it's actually a square of some kind. But now, so if we choose x and y to be the largest integers that are less than z, okay, then the largest integer of smaller than z is y to the n over 2, the absolute value, and they're less than z to the n when you do the summation. And then you take an example of 3, 4, 5 for n equals 3. Okay, so then I go through the calculation here, and what happens is when you do the calculation, and the absolute value of the number is different than the square root of the number, okay, then you get 25 plus 64 is less than 121, which is 11 squared. That's the example. So if x are the largest numbers possible, then every number that's smaller than that is still less than z to the nth. So there's no possible integer values that can equal z to the nth. And that proves Fermat's. Okay, thank you.